Hello everyone, welcome back. So once again we're going to be talking about these rigid body, free body diagrams. Goodness, rigid body, free body diagram. Body twice. So, rigid body FBD. There we go. So let's look at an idealized model. We have a pole and it's just sticking out of a wall. We have 1200 Newton force applying on it. Now I know this might seem weird. You're like, why a random pole? But we're mostly caring about these support reactions. You'll see a bunch of strange cases like this, but there are situations where you see things that are like this, even if they're not exactly the same. We don't usually randomly see an I-beam just sticking out of the side of a building. Or maybe you do, you know? Some modern architecture. Okay, so first what we do is we draw an outlined shape, which usually you can just, if you wanted to, you could have just drawn a line. There's not really anything super important with this. You don't have to be an artist to draw a free body diagram. If the dimensions don't matter for the cross-section, don't worry about drawing it. Just draw a line. Now, you need to make sure that this body is isolated. It's a free body diagram. That means that any place it attaches to something, you cut it. Achoo! And so now that I've cut it, I have to add reaction forces. Now, these reaction forces are going to depend on what it was. A cantilever beam, so a fixed support at the wall, it has three reactions. It has the reaction force in the Y, the X, and also the moment. So all three of those play into this. We then have to take into account its weight as well, because that is another thing that's acting on it. And we also need to take into account the applied load. Be very careful with the direction for this, because if you get it wrong, it can really mess up your answer. It doesn't matter too much when you have an unknown like this. If I draw the arrow in the wrong direction, I'll just get a negative number. But if I draw this arrow in the wrong direction, when I have the answer, when I know what the value is, then I will be messing everything up. Because if I'm looking at this, some of the forces in the Y direction, both of these are pointing down, so they should be added. If I did it wrong, then I would subtract them. I would get a much different answer. And also, please don't forget the weight of the body. That is one of the biggest mistakes people make, is they forget the weight of the body. Okay. And finally, you want to label your loads and dimensions. You need to have these dimensions because one of our equations is going to be sum of the moments. And so if I don't know how far to the free body, or to the center of gravity, or how far to that applied load, I can't do that. I also need to make sure I have a name for all my variables. You can just call this force Y, force X, force AY, force subscript AY, like I usually do this, something like this. But it really doesn't matter. As long as you're consistent and you know what you're doing, it's good. Just go with it. Now, once you have all this, you can begin to solve. However, before we jump into how to solve, because we've done that before, let's talk about different types of supports. Okay, support reactions are important because they show you how you're supposed to draw your free body diagram. If you draw them wrong, you're going to get the wrong answer. Now, luckily, they're given in your textbook in Table 5-1, so reference it. I let you use your textbook for a reason. But there's three that are used a whole lot. One is a roller. It means a roller can move back and forth, okay? And it can also rotate freely. What it can't do, though, is go into this. It's not a ghost roller. It can't magically go into the floor, so it's not allowed to do that. So as you can see, it will have a reaction force that resists it directly perpendicular to the ground that it's on. The second one is a smooth pin or hinge. A smooth pin or hinge will have a reaction force in the Y direction and the X direction because it does not allow that pin to move anywhere. It can still rotate freely, that's okay, but it cannot move in the X or the Y direction. And finally, a fixed support. Well, at that wall, nothing's happening. It's not moving because it's fixed. And because of that, I will have three reactions. One, the reaction force in the Y, the X, and it will also have a resistive moment. It will not want to bend at the wall, even if everything else is bending. And this is more or less what I've been saying earlier. If it prevents translation, you have a reaction force that's going to be perpendicular to that translation. Or sorry, that would be parallel to that translation that's resisted. If rotation is prevented, then a couple moment will be exerted to prevent that. Other things to think about, once again, you're probably like, when am I ever going to see a fixed support? If you have a very rusty hinge, or perhaps it can turn but with much difficulty, it's kind of like a fixed support. It will have a moment that is resisting up to a certain point, rotation, just not infinitely. I mean, even this beam isn't infinite. Eventually it's going to break if I apply enough force. Okay, so we'll stop there for now, and then after this we're going to go into an example where we actually try out using our new fancy free body diagrams to solve a rigid body equilibrium problem. So once again, there's 3 different basic types of supports, and whatever they resist, that's what they're going to have to create to stop that. Okay, so if they resist motion in the direction of the ground, then there's a reaction force from the ground. If they resist motion in both the x and y direction, there's a reaction force in the x and y direction. And if they resist motion in the x and y direction, and they resist any sort of turning, twisting, there's a reaction moment and forces. So whatever it resists, there has to be a moment or a force to resist. So I hope this helps you, and I'll see you all next time as we jump into an example. Bye-bye.